All right, we are now recording. Okay, so, like I said, 11.6 through 9, what do we need to talk about? Was this assignment as easy as the 11.4 through 5 stuff? Close? Okay. Good. Okay, does anybody need me to say anything about those concept questions, 6 through 9? Once. Twice. Okay, and then there weren't any multiple choice on this part, were there? Oh yeah, there were for 11.8, there was some multiple choice stuff, wasn't there? Okay, so how about module 11.6, the second law? 35? Watch me go. Sorry? Oh, thank you. I didn't even see him. Cool. 35, here we go. Okay, so 35 gives you this expression for the position at a given time. So it says that the position of some particle is 4t squared in the x direction minus 2t plus 6t squared in the y direction. And that gives the position of a 3 kilogram particle relative to the origin of an xy coordinate system where r is in meters and t is in seconds. A wants an expression for the torque, and then B wants to know if the magnitude is increasing or decreasing or whatever. Okay, so I don't want to say this without just giving you what I'm looking for. So we're trying to find torque, right? And torque implies that what thing would be happening? A rotation, but more specifically, unless the net torque is 0, it's rotating and accelerating. There's some angular acceleration, right? Okay? So we need to find a way to take this information and come up with an expression for angular acceleration, right? Does that follow? All right, so we're given this r. What's the connection between r and acceleration? What is r, you guys? Radius. It's radius, it's position in 2 dimensions, right? In other words, this is my horizontal position, and this is my vertical position, right? So I ought to be able to find my horizontal, if I take a derivative, what would that give me? Horizontal velocity and vertical velocity. And if I take yet another derivative, that'll give me my horizontal acceleration and my vertical acceleration, right? That feels like a good direction to go in. So I'm going to start there and see what that gets us, because I don't see what else we could do, right? We've really only got 2 equations for acceleration. There's I alpha. So I for us is going to be mr squared because it's a particle, right? And then alpha, well, we'd have to find alpha, right? Or we could try to do torque equals force times distance, but that force is going to be mass times acceleration, right? So either way, I'm left with, in some fashion, figuring out what that acceleration is. Follow? Okay, so that's where I'm going to start. And I think if you, well, I'm getting ahead of myself. Okay, so let's do that. So here we go. dr dt equals velocity. So that's going to be, let's see, 8t I, hate the stupid minus. I don't know what we got. So minus 2 plus 12t, I guess, j. Does that look okay? Everybody cool with that? All right, so that's my velocity to give an instant. So now I ought to be able to find my acceleration. So that's going to be 8i minus 12j, right? Cool. All right, so where do you guys want to go from here? So which solution makes more kind of intuitive sense, you guys? Doing well, actually, let me pause that thought for a second. I think because my radius and my force are not at right angles, I'm a little bit more comfortable trying to do this. Torque equals force cross radius. Doesn't that work? So I just need to come up with an expression for force. So, thank you. Yeah, yes, it's totally radius cross force. Thank you for catching that. I was half a second behind you on that. Okay, so I've got my radius already written out, so I just got to come up with an expression for my net force, right? Well, if this was my acceleration, just multiply by mass, right? So my net force ought to be mass times acceleration. So 24I minus 36J. Follow? And now we can just do our cross product. Good. So we've been using the Mary Shepherd method, right? Making sure I have the right Mary. So let's see. So we want R cross F. So that's looking like. Ooh, what am I doing? What's the question? It wants it after 3 seconds, doesn't it? Is that right? No. Find an expression for the torque. Oh, relative to time. Yeah. Okay. So we're okay. Am I nervous? Well, let's see what happens. I guess if I was here. Let me check my notes before I start going down this road and make sure I haven't made a mistake. Is this number 35? Chapter 11. Thank you for being patient. That is chapter 13, chapter 12, chapter 11. I'm just nervous about the t squareds. So I'm guessing they cancel. Yeah, they do. Okay. Okay. So here's what we're going to get. So I want to do R cross F, right? So let's see. So R is 4t squared is the x component. The y component is negative 2t plus 6t squared. And thank you, it is minus. Hang on. R cross F. Oh, I see what I did. All right. But yes, you are right. And I need to write this smaller, or I'm going to run out of room. So here we go. Try this one more time. 4t squared, negative 2t minus 6t squared is the k component, 0. 4t squared, negative 2t minus 6t squared, 0. And then my r, or my f rather, is this, right? So 24, negative 36, 0. 24, negative 36, 0. Cool? Okay, so let's see. So my I component is going to be 0, right? 0 minus 0. My j component is going to be 0 minus 0. So it's just a k component that I'm left with, right? Which, yeah, makes sense because it's got to be perpendicular to the xy axis, right? So what are we going to get? You're going to get 4t squared times negative 36 minus this mess, 24 times negative 2t minus 6t squared. You can simplify that. So you get negative 144 t squared. Let's see, this is going to be plus 48t. And then minus times minus gives you positive, so plus 144t squared. And the 144's cancel. So you get 48t, and that was in the k direction, right? Cool. All right. I wish there was an easy way to do those cross products. All right. So problems with that. All right. Then B says, what's the wording of it? Let me make sure I say it right. B says, is the magnitude of the particle's angular momentum relative to the origin increasing, decreasing, or unchanging? So it's asking you if the momentum is increasing or decreasing. And we just got 48t. So for any positive value of t, which is, a safe assumption, what's this going to look like? This is going to be a positive number, right? So what does that tell me about the momentum? It's increasing, right? You guys remember your net torque is equal to the rate at which your angular momentum is changing, right? So since our net torque is positive, our angular momentum must be increasing. Good. Alrighty. One other thing you could do, it occurs to me, is, and I don't know if this makes it any easier, the book solution did this. They did m times r cross v to find the angular momentum, and then they took the derivative of that to get the torque. But it boils down to the same thing. Okay, so that was 35. Questions about it before I get on? Okay, cool. What is that, 36? The belts. Cool. Okay, so 36. Let me see. The figure at the right shows 3 rotating uniform discs that are coupled by belts. One belt runs around blah, 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 blah. So we've got this. So we got a little wheel, a bigger wheel, an even bigger wheel, and an even bigger wheel. So we got a belt that goes around this guy. And we got a belt that goes around these 2 dudes. Like that. Let's see, our discs are labeled. We'll call the big one A, we'll call the little one B, we'll call the giant one C. We know this is rotating that away. Let's see, so what do we know? Disc A has a radius of R, and its hub has a radius of 1/2 R. So R, 1/2 R, crappy notation. This guy is 0.25 R. And this one is 2R. And it wants the ratio of the magnitude of the angular momentum of disk C to disk B. So, disk C to disk B, is that what I just said? Yes. So we are looking for the ratio of the angular momentum of disk C to the angular momentum of disk B. That's the thing we're trying to find, yes? Okay, so, make sure this is the way I did it before I start just talking. Oh wait, I need to know something about the masses, don't I? Does it give us anything about the masses? Oh, right, thank you. Okay, yeah, so we need to come up with an expression for the relative masses of these things. Okay? Disk B and C have the same density, mass per unit volume. Okay, so, thoughts about how we can use this information about the radius to find out something about the relative masses? Let's come back to that then. Let me do this. Check it out. So angular momentum of C. Well, that's going to be the rotational inertia of C times the angular velocity of C, right? And this is going to be the rotational inertia of B times the angular velocity of B, right? Good? All right. Well, both of these things are solid cylinders, right? So, where's my, oh, that's right, I moved it. Okay, so this is 1/2 the mass of C times the radius of C squared times the angular velocity of C. Yes, right, there's my I. And down here, I'm going to have 1/2 the mass of B times the radius of B. squared times the angular velocity of B, right? Good? All right, so we definitely have to come up with some sort of way to get these two masses to cancel out, right? So do you guys agree that the weight of each of these things, the mass of each of these things would be proportional to the area?
Yeah.
Okay, so how does that help me? Yeah, so the area of C would be 2 times pi times 2r squared, right? And the area of B is 2 pi times 0.25 r squared, right? So if I'm looking for the ratio, the ratio between their areas should be the same as the ratio between their masses, right? Because I'm stupid and the equation for area of a circle is not 2 pi r squared, it's just pi r squared. Thank you. Like I said, I'm having some Mondays today. All right, so are we good up to here? All right, you okay, Kurt?
Yeah.
I got you. I hope you feel better. All right, so does everybody understand that the ratio between the masses is the same as the ratio between the areas? So these pi's cancel, the 2's that I had in there would have canceled. My r's are going to cancel, right? So I'm going to get 4 over whatever 0.25 squared is. So what is that? A quarter of a quarter is a 16th, so 0.0 something. 0.0625 or 0.0625. There we go. So anyway, it's going to give you 64. So that's the mass of C over the mass of B. Follow? Okay, so that means I can cancel these guys out and make it 64. The 1/2s are going to cancel. So right now I'm looking. Is everybody okay with what I did so far? No. Bunch of algebra, right? So right now I'm just going to write where we're at now. We've got 64 times the radius of C squared times omega of C over the radius of B squared times omega of B. Well, I can do something with these radii, right? So this is 64 times, let's see, the radius of C is 2r squared. Oh wait, do I even do that? Yeah, well, whatever. And then this is 0.25 r squared. Does that give me 64 again?
Yeah.
Now I'm nervous. Is 64 times 60? Yeah, let's keep going. All right, so now I'm looking at 64 times 64 times omega of C over omega of B. Yes?
No, that makes sense.
Am I okay so far? Okay, so now we just got to figure out the relationship between the angular velocities, right? So we had done one of these before. Let's start with the angular velocity of B. It doesn't matter. You got to start with one or the other, right? Okay. So can I erase all this mess here? All right. So all right. So if I have the angular velocity of B, that's the same as the velocity of a point on the outside of B divided by the radius, which is 0.25 r, right? Does that make sense? Okay. Well, isn't the velocity of B the same as the velocity on a point on the outside of this little hub here? Right? Because remember, that whole red belt is moving at the same velocity, right? So that means the velocity of A over 0.25 r is that same number, right? Well, the velocity of A is equal to the angular velocity of A times that radius, which is 1/2 r, right? Follow? All right, so let's see, my r's cancel, and I get 1/2 over a quarter, which is 2. So this is 2 times omega A. And what's true about the angular velocity of the hub of A? That's the same as the angular velocity of the outside thing, right? So this is 2 times the angular velocity of A is the same as the velocity of a point on the outside of A divided by its radius, which is just r. Good? I know, these problems are tedious. I've seen them on AP tests before, though, so we got to know how to do them. All right, and then finally, the velocity of A is the same as the velocity of C. And the velocity of C is omega of C times the radius, which is 2r, right? So r's cancel out, and you get 4 times the angular velocity of C. So we just figured out that the angular velocity of B is 4 times the angular velocity of C. So divide this by 4, and I think you're there, right? So we get 64 times 64 times omega C over 4 omega C, which gives you 1,028, I hope. 1,024, really? 16 times 16, or 6, yeah, it should be 1,024, shouldn't it? Did I put 1,028 on the thing? Oh, beans. 64 times 64 divided by 4. You would think I would know my powers of 2. I don't. Okay, anyway. And that's what we were trying to find, right? All right, so here's the deal. That was a ton of algebra, and I hope we never have to do that again. This skill, though, we've seen this a couple times now. Why will it not scroll up for me? Am I dumb? I must be dumb. It's the only possible explanation. Whatever. The process of going from angular velocity to linear velocity to angular velocity to linear velocity, you need to know how to do that. All right? Okay, that took longer than I hoped it would have. What number is next? That's like 40 over there. All right.
Can we do 41 instead?
Do what?
41 instead.
So yeah, 40 is actually pretty similar to 35, except instead of taking the derivative, you take the integral. So for number 40, you just integrate, right? Because you're taking the antiderivative to find the change in angular momentum. So you integrate from 1 to 3, and you know that at time 1 you're at 5. So 5 plus whatever your integral is, and you're done. Is that okay? Okay. All right. And then 41, what is to be gained about going over 41? So calculating the rotational inertia, yeah, we ought to be able to do that. So yeah, let's go over 41. Okay, so here we go, 41. So we've got this shape. On one side of it is a little square, and on the other side of it is a hoop. Oh, this is another one where you need to get one of the equations out of your book. Remember I ran into that last chapter where the sheet I gave you wasn't complete? Darn it. I need to replace that rotational inertia sheet I gave you guys because it doesn't have all of them. I thought it did. Here's why I'm hesitating. So we on the sheet, you guys, that sheet that I gave you that has the rotational inertias, on there is the equation to find the rotational inertia for an object spinning like this, right? A hoop spinning about the center of mass. Okay. What's not on there is an equation to find this, right? Okay. And technically speaking, that's what we'd have to do here because we want this thing to be spinning like this, right? So what you'd have to do is you'd have to know the rotational inertia of it spinning this way, and then use the parallel axis theorem. Okay. So that's what that process would be to get this, okay? And honestly, I'd have to look it up. I don't remember what the rotational inertia about that point is, but it's, it's like whatever. It's 1/3 mr squared or whatever it is, 1/4 mr squared. I don't know, but it's something like that. And then you just do, plus nh squared. Follow? So that would give you the hoop, all right? And then this thing, the box, you have to break up into 4 chunks. What's the rotational inertia of this side? 0. Why? Because the radius is 0, right? Okay. This, because the whole thing is at the same radius, you can just do m times r squared. So whatever the mass of that side is, times r squared, that would give you the rotational inertia of this side. And then you're left with these 2 rods, and a rod is 1/3 mr squared. So you do 1/3 mr squared plus 1/3 mr squared. Okay, and you add those values together, and that gives you your rotational inertia. All right. Francis, is it okay if I leave it at that?
Yep.
Okay, so again, you guys, look, when you're finding rotational inertias, in the same way that you can add masses, you can add rotational inertias. And that's what this problem is meant to be about. And it didn't occur to me until this very minute that you guys were missing that one piece. So I think as long as you understand that you can add them like that, I think you're in good shape. Is that fair to leave it at that? Okay, thank you. I apologize. That's my bad. All right, so, and then you had said just go over 41.
That's the one.
Oh, that's the one we just talked about. What was 40? Oh, that was the one where we get it integrate. Okay, cool. 40.
That's beyond the multiple choice.
Okay, I got it. Okay. All right. So yeah, the next module is the conservation of angular momentum. We're definitely going to need to finish this up tomorrow. Like, it's fine. Let's get through what we can. So questions on those multiple choicey ones? Numbers 1 through, what were there? 10 of them there? Answers were on there. Everybody did okay with the multiple choice and or figured them out? Going once? Twos? Threes? Not a word? I'm sticking with threes. Alrighty. Ooh, that's just like one that I put on the test. Oh, alright. Ooh, now you're wondering which one it was. Kurt, what do you got? Which one? 50? Alright, and then we got 41 and, or no, what's that? 44, 47, and 50? 44, Texas cockroach. 47, the track with the train. 50. Ooh. Okay. I do want to do 50, but I think that I want to do 44 or 47 because I think those are a little bit more like stereotypical, like you're more likely to see one of those on an AP test. Yeah, 50 is a weird problem. And if I remember right, it's not nearly as bad as it looks, but let me hit the others and then. Let's see. Yeah, it's just conservation of angular momentum.
Yeah.
So convert convert 30 degrees for radians. Let me make sure that actually I might be able to do here in like 2 minutes. Yeah. All right, so here's all you do for 50. I'm going to do it. I know I just said I wasn't going to, but damn it, I'm doing it. All right, so here we go. So here's the deal with 50. It says the rotor of an electric motor has a rotational inertia. So the rotational inertia of the motor is 2 times 10 to the negative third kilogram meter squared. And that motor is attached to, I keep losing my spot. The motor is used to change the orientation of a space probe in which it is mounted. The motor axis is mounted along the central axis of the probe. The probe has a rotational inertia of 12 kilogram meters squared. Calculate the number of revolutions of the rotor required to turn the probe. So the idea is we're going to assume that nothing's moving. Okay? So our total angular momentum initially is 0, and that's got to equal our total angular momentum after we turn on the motor. So the motor is going to turn one way, that's going to turn the space probe the other way, right? So that it adds up to 0. Okay? So what that means is the angular momentum of the motor plus the angular momentum of the probe have to add up to 0. Okay? Well, let's see. Angular momentum, that's rotational inertia times angular velocity plus, right? So basically one of them is going to be positive, one of them is going to be negative. So just call them equal and don't worry about your signs.
I guess just think this visualizing comment was how
Yeah, so this is something that I've seen in a couple. This is going to be related, so bear with me for a second. Helicopters. Cool. Hello. All right. Helicopters look like that, but I'm missing something.
propeller on the back.
Propeller on the back. So think about what would happen. Suppose this was a helicopter. Okay? Well, when the blades, so everything's not moving, right? So I put the wheel away already. But so if the blade starts spinning this way, it's producing torque. What's it going to do to the body of the helicopter? Spin it the other way, right? Okay? So what does that other propeller do? Counters it, right? So the idea is the top propeller is going to make the body of the helicopter want to go like this, right? So this propeller here, this one, pushes that way to counteract the rotation produced by the top propeller, right? Okay? This is a helicopter without that.
Yeah, that's.
Does that help?
Yeah.
Exactly. Is that what they're called?
Yeah.
Oh, I didn't know that. I call it big propeller, little propeller. And then they have those army propellers, or army helicopters that look like this. They rotate opposite directions, don't they? Right? They have to.
And then Russia made ones that have two right next on top of each other, so it's going to.
Oh, that's cool.
So they don't get it.
Nice. That's cool too. Okay, so are we good with 50? All right. I don't think I have time to do 41 or 44 here in 3 minutes. You know what? I have time to do 44 real quick. We got 5 minutes. All right, 44. So we've got a Texas cockroach. So the mass of the roach is 0.17 kilograms. He's running counterclockwise around the rim of a Lazy Susan, which is a circular disc mounted on a vertical axle. It's a little spinning turntable thing. Okay? So it's this. Right? Okay? Let's see. So we know that the radius is 0.15 meters. We know that the rotational inertia of the Lazy Susan is 5 times 10 to the negative third kilogram meters squared. Frictionless bearing. The cockroach's speed relative to the ground is 2 meters a second. And the Lazy Susan turns clockwise at 2.8 radians per second. The cockroach finds a breadcrumb on the rim and stops. What's the angular speed of the Lazy Susan after the cockroach stops? So, let's see. So what we need to do is this. We need to write an expression for our total angular momentum while the cockroach is walking, and set that equal to the total angular momentum after the cockroach stops walking, right? Because everything there is going to be internal, right? Follow? Because all of the torques are going to be either the roach pushing the Lazy Susan or the Lazy Susan pushing the cockroach, right? Okay, so this means that we want the angular momentum of the roach initially plus the angular momentum of the Susan initially to equal the angular momentum of the roach final plus the angular momentum of the Susan final. So this looks to me like it's going to be the mass of the cockroach times the radius. Where's he walking? Is it the outer edge? He's walking around the rim. So 0.15 is our radius, and his velocity is 2 meters a second. So that's the angular momentum of the cockroach. Which way is he going? He's going counterclockwise, and the Lazy Susan is going clockwise. So I need to make one of those negative, right? Usually we use counterclockwise as positive. So I'm going to leave that positive, and I'll make the Lazy Susan negative. So the Lazy Susan ought to be its rotational inertia times its angular velocity. Follow? So that's before he stops walking. All right? After he stops walking, what's going to be true after he stops walking? We're going to have the same angular velocity, right? So I need a way to rewrite. I mean, there's a few ways you can handle this. I did MRV before. Isn't that the same as mr squared omega? Right, if you replace v with omega r. So this becomes his mass times r squared omega plus 5 times 10 to the negative third omega, and then solve for omega. No. If our omega comes up, if we have an answer of negative omega, that means that at the end it was spinning clockwise. And if we get positive, that means we're spinning counterclockwise. So, yeah. Does that make sense? All right. More tomorrow. Test Wednesday. Yes.
If you're in on this, we'll talk about it here.